you for the introduction, and I'm really happy to be part of this talk series. Seems like it is largely the ICER community which is involved, but um, I'm not sure uh, like who's running this right now, but would love to learn more about the um, team that is organizing this as we go. I want to talk about elections as complex systems today. I did see that there was some interest in understanding complex systems. A lot of it from the biological side in this talk series, and I wanted to offer like a complementary perspective of how other types of systems can be viewed as complex systems, and point out how very similar tools can be used to look at all of these different settings. Specifically, I want to talk about voter turnouts, victory margins, and universality, which is based off of some recent work that we've been doing. And I will explain, if any of these words don't make sense to you right now, I will explain what they mean as we go. So the plan for today is that we start with maybe some motivation, discuss certain results and applications, and then it's open for discussion. But before we go into the talk, I just wanted to give you like a brief background to myself. Like I spent 10 years at ICER Pune doing my bachelor's, master's, and PhD. And I started as a postdoc last year. And most of my work can be categorized into three themes. The first theme is partially observed complex systems, where I, try to understand what can we understand about an underlying system that we don't have complete information about, or that we can't fully observe. And given that this thing is called like fishes, I think ecology is a great example where you have a lot of partially observed systems. You want to manage ecological systems, but you don't have complete information about them. So how do you make decisions about such systems, about managing such systems? The second part of my work deals with rare events and extreme statistics. Um, I think we're all familiar with rare events, and especially extreme events, which are sort of events that don't occur very often, but when they do, they can have a lot of disastrous consequences, like floods or droughts or earthquakes. And there is a very beautiful theory for dealing with extreme values of independent, identically distributed random variables. But when you start introducing correlations like there is in real data, we don't have many tools. And like that is what this part of my work deals with, trying to build theory to study correlated extreme events. And finally, something that I won't say much about right now, because the whole talk is about it. I am interested in understanding cultural evolution and social dynamics. More importantly, like how do certain large scale patterns emerge from, the kind of messy social dynamics that we see. And I often um, sort of present my work or my research program as the study of messy complex systems, where we want to go beyond, certain assumptions like, I think by now it is clear that we have to go beyond linear dynamics and start looking at nonlinearities to understand realistic complex systems. But the jump from equilibrium to non-equilibrium systems is still a huge jump that we know very little about. And making essentially, instead of looking at steady states, we should also be looking at transients. Instead of looking at IID data, we need to look at what correlations mean. And one thing which I think is often forgotten is that instead of looking at just averages, we need to understand full distributions and the consequences of what broad distributions around an average can mean. On this note, let me just start this talk about one of the messier complex systems that I know, which is democratic systems. And I want to start with addressing this very simple question about why we should be studying elections in a very um, so I think elections are very interesting from just the scientific viewpoint. Um, Given that they're this large scale collective decision making experiment, there are many underlying processes which govern elections. Like, okay, there is complicated opinion dynamics, there are social networks at play, and that leads to people forming opinions about their electoral preferences, which then translates into one vote that they give. And it's an exercise where many people come together. And in fact, we started this work around the time, so a couple of years ago. And last year, 2024, was called the ultimate election year, where 64 different countries had their general elections, including India and US. Over 2 billion people came together to vote, and it just seemed like, you know, the right time to be maybe thinking more closely about the science of elections. um, Given that I'm at the Santa Fe Institute, I am mandated to say that, oh, there is like elections are a system of interacting units which lead to emergent phenomena, and definitely like a great example of complex systems. And finally, which is, maybe true, um, maybe elections have real world consequences too. And that is why we should probably spend some time thinking about them. Maybe not in the way that I'm going to think about elections today, but maybe that is useful too. I just wanted to point out that, like, if you're interested in complex systems, there are many offshoots of, like, there are many underlying processes and dynamics that are going on which govern the final election unit. So, for example, cities have, all sorts of dynamics where there is segregation, there is, inequality, there are social networks which inform our decisions. There are opinion dynamics which are informed by, the cities that we live in and the social networks that we are situated in. And all of these themes are going to be relevant. I won't necessarily touch on them right now, but if you want to, start thinking about elections, these are things that you should be thinking about. I feel like a bigger theme of my talk is going to be simple models of complex systems. And more importantly, like, what does it even mean to have a simple model of complex system? And if it turns out that a simple model is able to tell you something about a complex, like if it is able to reproduce certain features of complex system, what does that really mean? And how can you use that to make any to infer anything about the underlying complex system, which may not necessarily be following the dynamics of this simple model? Okay. So let me just start by discussing what I mean when I say an election. But because, elections have very different formats in different countries, and in this talk, when I say an election, uh, I mean this. So we have some piece of land which is broken up into many small electoral units. Um, and each electoral unit, so if we let's say look at electoral unit I, it looks like this, where, there are some candidates which are contesting the election, and there are some number of people that turn out to vote, right? So let me just say there are some CI number of candidates in electoral unit I, and the voter turnout is capital TI. And each voter is actually thinking that, okay, I need to vote for this one person, and they cast a vote. And what I'm interested in this talk at least, is competition in elections. Like what do we mean by a competitive election? What do we mean by a landslide victory? So one thing that we started thinking about was the margin of victory. So in electoral unit I can define the margin of victory as the votes received by the winner minus the votes received by the runner-up. So the highest number of votes, so the candidate with the highest number of votes, so the votes that they get minus the votes received by the candidate with the second highest number of votes. So the difference between the top two, essentially. And this is a measure of competition, as you can see, in the sense that if the margin of victory in that unit is very, very high, then it was an easy victory for the winner. But if the margin of victory is small, it's close to zero, then it was a very closely fought battle. But the margin of victory is not enough for us to measure competition. And let's just understand this through this simple example where, suppose we have these two units, this pentagon and this triangle. And I tell you that the margin of victory in this unit was 160, whereas the margin in this unit was 1,200. Like, one would be tempted to say that, oh, this election was more competitive than this one. But we also need to look at what the turnout in all of those elections were. And now, when you put that in context, which is like, okay, a margin of 160 with 180 people turning out seems to be more of a landslide victory than the counterpart away. Right? So I just wanted to point this out to say that this is just an intuition for this margin by divided by turnout being sort of a potentially useful measure for studying the competitiveness of elections. And you can define so for each electoral unit I, you can define the margin divided by turnout. So for each unit I, you have like a number associated with it, which is the margin divided by turnout. And then you can plot a histogram of all of these margins by turnout, or the probability distribution of this, and we can see what it looks like. And if anyone has trouble understanding what a histogram or a probability distribution is, like let me know and we can go over it again. But what I'm just doing is like making a histogram of these numbers across the different units. And in these units, often, like in India, these units mean constituencies for us, but there are also like different levels of, units. Like you can think about polling booths, you can think about assembly level constituencies. Um, so this sort of definition holds at all scales. And let's just stick to the constituency level discussion right now. So I want to talk about result one um, of this talk, which is when we plotted the distribution of this quantity margin divided by turnout and scaled it by the mean so that all of the distributions have the same mean. Um, and the data over here corresponds to 32 different countries across 5 continents. So histogram with the same color corresponds to data from the same country. And we were looking at the distribution of this quantity across countries with election data aggregated over the years. And we saw that all of the distributions seem to be behaving in a very similar way. There is like a trend that they're following, and there is some noise which I can speak more about. Often it is associated with not having too many. So like India is a very big country, and I can show you data for India alone. But there are smaller places where there isn't much data available to make these histograms, so there is noise associated with it. Um, but there seems to be like a trend to this the distribution of this quantity, which does not depend very strongly on which country we're looking at, what the context of that election was, and so on. And the big red circles here are just, like I combine all of those histograms, aggregate them, and this is the combined data. So this seemed striking to us. Like,
Can I
why is
ask
there
what the y-axis is?
the y-axis is just the probability density of x. So x is the value of this quantity, and y-axis is just the probability density of that
Okay.
of this indicator taking that value. So this is essentially a histogram. Does it make sense, Veva? Okay. Um, yeah. So this seemed striking to us, and we wanted to explore this further as to like why this may be happening. So given that we've now set up the structure for an election, let's think about what a model for an election can be, right? So let's just start with what we would think as a null model or the simplest model to think about, which is that okay? Let's say there are three candidates that are voting that are contesting this election, and we fix the number of candidates in each electoral unit to be three. Let's just start with that. An important component is that there is a voter which is trying to decide who they want to vote for. And as you can see from their expression, it's a very difficult decision often. So, what this voter does, let's say, is that it draws a random variable uniformly between 0 and 1 and assigns a weight to each of the candidates. And then, because they're smart and they know that probability should be normalized, they just normalize those weights to get the probability of voting for a candidate. So, for example, in this case, like if the weights were W1 for the first candidate, W2 for the second, and W3 for the third candidate, the voter votes with probability P1, which is given by this formula over here, to candidate 1, votes for candidate 2 with probability P2, and votes for candidate 3 with probability P3. As you know that there are many voters in a given electoral unit, And we just say that in a given electoral unit, everyone votes with the same probabilities, P1, P2, P3. But as we move to another electoral unit, in an election in another unit, we just repeat this process of drawing random variables, assigning weights, and voting within that unit with those probabilities. Okay. So if like you are more mathematically inclined, you can look at this. So this is just what I described. Like this is the voting. So this is the probabilistic voting rule that we are working with, where within the electoral unit, everyone votes with the same probabilities, which are given by these uniform random variables and then normalized. And an important assumption here that we are making is that each voter, even though they might be voting with the same probabilities, are voting independently. So this is a null model in many ways, in which we are taking away preferences of people and being like, okay, let's see if what happens when these things are distributed randomly. Um, but also we are taking away interactions between people, which is an important component, I would hope, in elections, where people do learn from each other and think about what other people are saying and then cast their final vote. In this model, one thing that we do is we take the voter turnout to be taken from the real election data. So you have elections where there are many different units. In each unit, there's a different number of people that turn out to vote, and we take that number into our simulations. And you can ask me later, why is this important? It is not important for some things, but it is important for some other things, and I'm happy to explain why. But this is just what it is. Like we are taking the input from empirical data. And you might think of this as like a really stupid model, and we didn't want to call it the stupid model, so we just called it a random voting model. And I might refer to it as RVM in later slides, I'm not sure. But the question that I wanted to ask was, is the random voting model any good? Like when you're defining this, and what can this, like now when we run this model, when you simulate this model, or when you mathematically solve this model, what does it give? So this was result one that we had just discussed, of the distribution of normalized margin by turnout being sort of universal. You see a statistical regularity across countries, across cultures, across decades. And when you run this model, the random voting model with the real turnout data, it seems to be capturing this statistical regularity very well. And the turnout data that I gave to this model was the aggregated turnout across the elections that I'm using over here. And it seems to be matching the aggregated data very well. I also have results for, like what happens for single countries. And if you just use turnout for a given country, it is able to reproduce the trend for that country very well. And given that the random voting model is so simple, like you can also do a lot of math with it, and solve it analytically and get like the functional form for what this curve actually looks like. And I have some, we can also discuss um, what it means to have this curve. But how you compute this curve is interesting, because it connects to a strand of extreme value statistics called order statistics, which is the mathematics of ordering and ranking, which is very interesting. So maybe I'll just give you like a little bit of intuition for that. Um, Let me first give you some intuition for why this universality or statistical regularity emerges in the first place. All right. So we had this picture about this confused baby trying to decide who they want to vote for. They're voting with probability P1, P2, P3, and everyone in that county is voting with the same probabilities. So on an average, you would expect, if the turnout is T, you would expect that candidate 1 gets P1 times T, the number of votes. Candidate 2 gets number of votes equal to P2 times T, and P3 times T for candidate 3. And there are, of course, going to be fluctuations around it, but on an average, this is true. Right? So let's say P2 was greater than P1, and which is in turn greater than P3. Then we would call the margin of victory would be how much votes did this person get subtracted by the number of votes that this person got, right? Which is just P2 minus P1. And now if you just look at margin divided by turnout, it only depends on this the gap between the probability of voting for the top two. It has no dependence on the turnout itself, which is one reason why, like different countries have different turnout distributions. But when you look at this quantity margin by turnout, it seems to be not very closely depending on the turnout statistics. All right. But so it depends on the difference between the top two probabilities, but how do you compute that? And that is where, the field of order statistics comes in. So just a quick primer: if you have n random variables which are um, independent and identically distributed, drawn from this distribution P of x, then we know that under some mild assumptions and scaling, the sample mean of this will be just a Gaussian distribution with mean 0, variance 1. And that is what we know as the central limit theorem, the celebrated central limit theorem that we learned in school. But another question to ask is, what is the distribution of the sample maximum if I have n random variables? What is the distribution of the maximum of all of those variables, right? And you can imagine settings where you would be interested in that. For example, if you're trying to build a bridge over some troubled waters, like you may not only want to know the average height of tides, but you may also want to know in the last 30 years what has been the maximum height of tides, just so that you have an idea for how high you should be building a bridge over there. And as it turns out, even the distribution of the sample maximum under some scaling has a very beautiful limit theorem, where the distribution of the maximum under some scaling can go to one of these three universality classes instead of just going to one in the central limit theorem. It has three possible universality classes: the Gumbel, the Weibull, and the Frechet. And which one it goes to depends on the tail of this distribution P of x. So if P of x has a heavy tail, you go to Frechet. If it has an exponential tail, you go to one of the two over here. And if you have a finite cutoff, you go to, yeah, so depending on what type of tail you have, you go to one of the three universality classes over here. And like one would think that this would be called the extreme value theorem, but it is actually called the Fisher-Tippett-Gnedenko theorem, which is a sad story. But the thing is, we may not only be interested in the sample maximum, we may also want to know the full ordering of the random variables. Like we may want to know the joint distribution of the maximum, the second maximum, the minimum, the one which is just higher than the minimum, and so on, like the full order. The real challenge here is that even when you have these IID random variables, when you order them, they are no longer independent. Their distributions are, no longer. So first of all, they don't have the same distribution anymore. The minimum has a different distribution from the maximum, and they also now have correlations between them because we know that the maximum has to be greater than the minimum. So when you order IID random variables, they're neither independent nor identically distributed, and it poses a lot of mathematical challenges. And that is the sort of question that the field of order statistics tries to deal with. And using some ideas from here, you can compute the distribution of the difference between the top two random variables that we were discussing, P2 minus P1, and get this analytical form over here. And for the simple three candidate case, the distribution is shown to be something like this. But there's a very interesting limit. When you take the number of candidates also to be large, then this curve is actually just a simple exponential with mean 1. And that is a figure that I'll maybe show you in the end. So there's a lot of cool math to be done here with this very simple model. And that is one of the attractive features of this model. So here is like, just a plot of, just the random voting model simulations with a bunch of different turnout distributions. You see that the big circles here correspond to the different turnout distributions. And there doesn't seem to be any strong dependence on them. All of them seem to be collapsing very well on this analytical curve. But when you take realistic numbers in this random voting model, you do see like deviation, like realistic value of turnout and realistic value of number of counties. And then you make the histogram. You do see like a lot of fluctuations around this trend, which is also evident in real data. So it does seem to be capturing certain features of elections, and like you may be thinking at this point, so what? Um, what more can we say about elections from this? Given that the model is so simple, we can now start to probe the model mathematically and see what it can tell us, and then go back and check real data if it seems to have any bearing on reality. One thing that we were able to prove mathematically was that the tail of the turnout distribution governs the tail of the margin distribution too. Um, for example, like if there's a power law tail for the turnout, the margin will have a power law tail too with the same exponent, and so on. And that is something that we see in real data as well. And this is just one example, but you will see that the tails of margin and turnout seem to be very closely related across the board. Um, you may be like, okay, so all this while we have been sort of um, scaling the margin by the turnout, but I may just be interested in the margin of victory as it is. So if we scale the margin by the mean margin so that all of these distributions have mean one, and we take real turnout data for different countries, which look very different for different countries, this model is also able to just reproduce the scaled margin distribution in all of those different countries, which are actually not universal curves. They have very they have very subtle dependencies on the features of the turnout distribution. But as you give that as an input to the model, it is able to show up as a consequence in the distribution of the scaled margin as well. Here's the result that I want maybe you to think about, which is like, when we were looking at data, so I said, the data I was showing you was from 32 countries, but actually I looked at 34 countries when I was doing this study. And there were two countries which seemed to be behaving in a very different way. Specifically, Belarus and Ethiopia had this, qualitatively different features than what the model predicts, or than what every other country has been showing over the years, over several decades of elections. Um, and when you now go back and look at those elections, there is evidence and several scholarly articles, several news reports, several surveys from people on the ground that those elections have had a lot of either military interference in the case of Ethiopia, or just undemocratic practices. But these are not cases where there is such blatant evidence of fraud, but still, like this sort of deviation from uh, the standard trend that we were seeing could potentially signature something abnormal happening. And it could be used as a flagging tool. Like, okay, if you want to look into certain elections, this is just a flagging tool for it. This is not making any conclusive claim, but just like maybe keep this in mind when you're looking at election data. And so, yes, so maybe the deviations from this universality can help us flag electoral misconduct. And I want to maybe stop here and just quickly summarize, what we've been talking about, and open the floor for discussion. So the first thing that I want to point out is that, okay, elections, are definitely complex systems. There are many complex underlying processes which eventually end up um, reflecting in the election results. But somehow there seems to be an underlying order, at least in fair elections. And I say order in fair elections because we have seen that when this order has been broken, there has been evidence for like massive interference in those elections. Despite this, like the claim is not that the random voting model is the true mechanism by which every country votes and every person votes, but rather it provides um, a way of thinking about how such a regularity can arise. And it also shows you that maybe the statistical regularity that we are seeing is independent of the fine details of the elections that are happening. And when we aggregate all of these opinions and aggregate the votes together, maybe the fine details are getting washed away, and what we're left with is just something that can also be produced by a null model. The RVM also makes a lot of, so I discussed with you, some useful predictions, like like the scaled margin distribution, but there's like another complete set of results that you so another complete set of things that the RVM produces. It Let me just say that it reproduces features of election data more than I would have liked to see. And so we wrote like a follow-up paper on this on this work that I presented, which is titled like "Voter Turnouts Govern Key Electoral Statistics." And it just turns out that the RVM coupled with the turnout data of different elections can help us reproduce a lot of different features. And we want to use this as an appeal to the Election Commission in India for sure to make election data more freely available at the time of election, because even to date, the election data for the 2024 Lok Sabha elections aren't at the fine level of polling booths, even though they're mandated to be, like there's a form that has to be filled by every polling booth, which has to be made public. It's still not available in a way that is easy to access. And I want to close here with a couple of puzzles. And one of the puzzles is from, like my dear state of Maharashtra, where this is from their last election, which said, Maharashtra sees highest turnout in 30 years. Victory signs say both parties. Um, so we have spoken about how turnout can help us, reproduce these features of elections, but can it also help us signal like who is going to win? So if you have noticed, like margin that I've been studying here is just a positive quantity. But there is a systematic way to assign a sign to margin, which is like if the incumbent party is winning, then that's a positive margin and everything else is a negative margin if there's going to be a regime shift in that seat. And that is something that I'm looking into right now, especially because there is a lot of political science work on what turnout means uh, for uh, how can we infer the mood of the nation from the turnout distribution. But there isn't any consensus on what it really means. And this is just one direction that I find very interesting. And one puzzle that I want to leave you with is like, what does it mean when such simple model uh, capture some key trends in complex systems? And like, what are the inferences that we should be drawing from them? To what extent should we, using their results and thinking of them as the truth? And how can we be more careful about modeling choices is a broader theme, which is not something that I necessarily spoke about over here, but I think is very important as we start thinking about social systems. Just something to keep in mind throughout. And on that note, I would just maybe want to stop here, open the floor to questions, discussion. Happy to chat about anything.
Okay, thank you very much for the talk, Anjaneya.
Of
So
course.
for questions, feel free to raise your hands and then I'll go one by one through you guys. अरे स्वस्तिक चैट में जाके देखने रिएक्ट में होगा आप देखो स्वस्तिक if you want to ask a question, okay, I'll put you after. Dhruv, go first.
Yep. Hi, can you hear me?
Yep.
Yeah. Hi, Aanjaneya. Really nice talk. I wanted to ask one question regarding one of the last slides where you showed the Ethiopia and Belarus results. Uh,
Mhm.
uh, both of these countries are like very completely autocratic countries. And so my question was, can you use this model to flag like any electoral fraud in cases where it's not autocratic countries? Because in autocratic countries, you will get a huge margin difference. But in democratic countries, the difference might not be that much. So does the model help in flagging those kind of elections as well?
So if So technically, I think Belarus is still a democratic country. Like they do have democratic elections, is what I mean by that.
Yeah.
And like, but yeah, like there, it's very questionable. And if so, in the cases that we have seen so far, we haven't seen a lot of deviations from this universal curve. And in the democratic countries, that we think of as democratic, like maybe the US or India, it seems like these trends are being followed very well. And I would just point out that the fact that there is no deviation doesn't necessarily mean that there is no fraud, but it seems convincing that if like it seems from the data I've seen, it seems convincing that if there is a strong deviation, that means something very unnatural is happening. But there can still be fraud, especially at very local small levels, and that doesn't reflect in um, deviations from this universal curve. So that's like a question about false positives and false negatives. Um, and I hope that like if in a democratic country there is something which is strange that is happening, we will be able to flag it using this. But that is just a speculation. I don't
Okay.
think there have been very very strong cases of clear electoral fraud in the last few years.
Okay. Okay.
Okay, Shatadru, you're next.
Uh, Hello, thank you for the talk. Am I audible?
Yeah.
Okay. So I have two questions. One of is like, what happens if you like make the turnout number to be a fixed value rather than taking the empirical data? So
Mhm.
like, do you get the same curve or?
Just 1 second. Let me go back to this slide here. Yeah. So if I take the turnout to be the same value, or if I take it to be a uniform distribution, Gaussian distribution, or power law distribution, the scaled quantity margin divided by turnout, like under scaling,
Mhm.
still gives you the same um,
Okay,
uh, uh, curve for that quantity. But when you now look at the margin distribution, that becomes very different.
I see.
Um, yeah, the universality still holds. So, for example, so the claim is that you take any so in this model where there is random voting, you take any turnout distribution, which can be a delta function like you're pointing out, or any other distribution like a power law or a Gaussian or uniform. You run this model and you plot the distribution of margin divided by turnout. It is
Mhm.
going to be this curve,
Okay,
and that is something that you can prove.
I see. Uh, Also, like, have you tried some other model with like local interactions maybe between the voters, and
Yeah.
if they fall on the same curve?
So I've tried like a lot of variations of um, this model, like which having different probability protocols and so on, and they still seem to be qualitatively reproducing this trend. Now, let's say the problem with models with local interaction. Let's take so you use the word voter. So are you familiar with the voter model?
Yeah, like I have worked with like Deepak Bhatt, if you know.
Okay.
Yeah,
Yeah. So my complaint about the voter model is that it is not a model for voting.
yeah,
Unfortunately, it is a model
yeah.
for opinion dynamics mostly.
Yep, yep.
So if we want to, let's say, use it to make like a model for voting, we will have to evolve the voter model for some time and then stop it at some time, and
Hmm.
then be like, okay, how many people are of this opinion? How many people are of this
Yeah,
opinion? And then be like, okay, these people are voting for this party. These people are voting for this party.
yeah.
But that the stopping time is arbitrary, and there didn't seem to be like a very systematic way to um, resolve this issue, and that is why I stayed away from this. But I think like just 2 days ago, there is a sociophysics group in India which posted a follow-up work on this where they're trying to use a um, more detailed model for opinion dynamics for voting to
Hmm.
interpret our results. And I can share
I
that
see.
with you at some point if you just send me an email, and
Okay,
we
okay.
can talk more offline.
Yeah, sure.
If you have any comments about how the voter model can be used for voting, I would be very interested in hearing that as well, because it's such a bad name.
Yeah, I agree.
Yeah.
Yeah, that was it.
Okay, thank you so much.
Abhishek, you're next.
Hi, Anj, can you hear me?
Yep, I can hear you.
Oh, yeah. So the talk was very nice. I have two questions. So, towards the end, where you were talking about this follow-up paper, so you showed
Yeah.
that you were showing the plots of each of the countries. So, instead of a smooth curve like that, what you're showing on this screen right now, you had some deviation. For example, if you consider the US dollar thing, then
Mhm.
there was a dip or something. What is that dip coming from? And why is it this dips appearing in the earlier plot that we were discussing throughout the talk? Like if you are
Yeah.
incorporating the voter turnout data there itself.
Yeah. So the smooth curve that we were showing was for the margin divided by the turnout,
Okay.
whereas this figure that you're talking about, which I also flashed in the
Oh,
end,
I see.
is just the margin distribution scaled by the mean margin.
Oh, I see.
And so when you look at that, so you look that there's a dip in the margin distribution, and that is a feature. So now if you go back and look at the turnout distribution of the US, there seems to be a dip here as well. And so the turnout distribution, sort of the features from the turnout distribution magically seem to be carried over to the features of the margin distribution, is result one. And I think more magically, they seem to be canceling out each other and resulting in this universal curve when you just divide the margin by the turnout.
Right. But is
Why
this
is Dhruv
the
raising his hand
mapping?
again? I don't know. Okay.
Sorry. Is this mapping very like you can uh, like write some analytic formula to this mapping, or you just know that there is a dip in turnout distribution, that's why there is some dip in scaled margin distribution? Is this
So
relation very explicit or?
So the relations that have been explicit are mostly asymptotic. So for example, the tail of the turnout distribution often looks very similar to the tail of the margin distribution.
Okay.
And those things you can prove under certain assumptions. But features like a dip here carrying over into a dip here is not something that I've tried to prove. Um, the way I would do it is like try to have a bimodal distribution of turnouts and then see if the margin distribution is bimodal too. Like that is like a very simple model of a dip.
Why
Um,
bimodal?
just so that there's a dip here in the middle,
Oh, I
like
see.
between the
Okay. Okay.
yeah.
Mhm.
Because I don't know any other decent, like a simple form for a distribution with a dip
Mhm.
off the top of my head. That's why I just thought, okay, I will maybe compose two Gaussians together, and that might be easier to deal with analytically. And maybe there's scope for proving something about like bimodal distribution of turnout leading to a bimodal distribution of margins. But that's just a guess.
Mhm. Okay, so I have one more question. So there is this deviation that you're taking towards the tail, right? So uh, I was just thinking about that. Where can the deviation come from? Would that deviation come from the way that voting takes place? Like, for example, uh, for in India, if you in the constituency, this they just select by the simple majority. But in other countries, you have different methods to pick out this the winner of the election. So do these tail also depend on those features, or I mean, what can go into determining the behavior at the tail, the deviation at the tails?
And can you like point out specifically what you mean by like deviations at the tail, like in this figure?
As in like maybe not this picture, but can you go back maybe where you are showing the
Okay.
actual?
The universal
Yeah,
curve, yeah.
for example, like here you are seeing toward the end that green dot are like on the horizontal, like they have a lot of big distribution, right? Deviation from uh, the 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 analytic or the average curve or aggregated curve. So, like, what kind of things might go into determining that deviation? I'm just trying to think about that.
Yeah, no, I think that's a great question. And you're right in saying that, probably any deviation from the null model um,
Mm-hmm.
means that, like, okay, we have ignored a lot of things in the null model, and the deviations could be arising because, one or a combination of those things. So, for example, interaction between people or non-probabilistic voting and things like that. But I'll just point out that, the horizontal green lines, green points that you pointed out over here, are just because those are data of a country where all of those bins just have one data point. So now they're just coming out with the same density in this. But
Okay.
maybe if we just had more data in some way, or if we had finer data, for example, instead of looking at constituencies, we had polling booths. It could. My hope is that it would be similar to, like, the deviations of the tail would be lesser. That is what we see for India. And the archive paper that I mentioned does have like a lot of India specific results too. So you can take a look at that as well. Um, but it's a feature of everything that you said, which is feature like real elections being there being all of these different processes involved there, but also of just there is not a lot of election data that we have access to.
Okay. Yeah, that makes sense, I think. And just one more question, if not taking time, what is the GT in this plot that you are right now showing? This
Oh,
insect plot?
yeah, the GT here is just the density of the turnout. So
Oh,
the
exactly
probability
what you showed
density.
later, kind of.
Yeah, so it could be like a power law, it could be a Gaussian, it could be a uniform, and
And
that
all
is
of
what
them
I'm.
collapse on the same
All of them collapse on the same.
universality. That is kind of universality here.
Yeah.
Yeah, okay. Okay, great. I think my questions are answered. Thank you.
Okay. Thank you so much, man.
Fantastic. Swastik, you're next.
Yeah. Can you hear me?
Yep.
Yeah. Hello, Aanjaneya. Really nice talk. So I have two questions. So the first is so one of the assumptions I'm a little concerned about is so do we still see this universality in this for the distribution of this quantity when the number of candidates, or let's say the number of competitive candidates, is not constant across the whole, across the like whole country? Let's say, like, for example, in India we have certain states which are two parties, like de facto two party systems, certain states which are more than that, certain states which are one party systems. And so do we still expect this quantity, the scaled margin to turn out, like, do we still expect it to follow this distribution?
So let me answer it in two ways. One is that when I was showing you like this data in the beginning, like the first slide that I had, where we did not have where we hadn't even introduced the model. It was just real election data, which has all of that messiness already encoded, which is like, okay, different constituencies will have different number of competitive candidates. And the regularity sort of emerges despite all of those. So the regularity emerges from the election data first, and then the model comes next. And in the model, there is the simplifying assumption that we are making to do the calculation, which is that, okay, every constituency has three candidates, which was just like, okay, like there are two competitive ones, and then there's a third front. So it could be like multiple people combined together, or just one, semi strong third front. And there's a probability, and there's a chance that the third person gets a very small probability of voting. Of course, that's like a low chance, but it is allowed within the model. And now, if you look at this figure over here, which is Japan tends to have, 6, 7, 8 very competitive candidates in each of their electoral units. And their elections are, fairly different. And, India, like you said, has often two, but maybe sometimes three. And US is mostly just two competitive candidates. So the answer to the first question is, in the data, and in the model, even if it's not a fixed number, you do end up seeing the universality, you do end up seeing the statistical regularity. All of these plots have, and the model, so the dots over here are like real election data, and the solid line is the prediction from the model. And all the model predictions are from simulations with fixed number of candidates equal to 3. Which is not definitely true definitely not true for Japan, because it has many more competitive candidates. but it seems to be reproducing uh, the data well. There are there are certain measures to compute the effective number of candidates in like or effective number of competitive political parties in an election, which certain political scientists have worked on, and you could try to use their um, numbers and see what happens when you now simulate with a non-integer number of this. Like, okay, some constituencies have 3 candidates, some have 2, so on an average it is like somewhere between 2 and 3. um, and I expect that the universality will still hold. Whether it will uh, reproduce the margin distribution as well as it is doing right now, I'm not completely sure. But it's something that we can check for sure. But are you
Okay.
convinced by the idea that the universality does not depend on the simplifying assumption of fixed number of candidates? Because that's something that we're actually seeing from the data.
Like, thanks. That's indeed very interesting. So the other thing it's more like I want to ask your opinion